Okay, so um, let's talk about kinetic energy now. We did the potential energy due to gravity. We'll talk about the other kind eventually. So you have your potential energy. So now let's talk about kinetic. Kinetic is just when it's moving. Now, we're going to actually end up using this to describe that. Let's talk about this. Let's say that you have an object, it just starts right here from rest. So no kinetic energy. Kinetic energy would be non-existent. And then for some reason it's moving. And at the end you know that it's moving, right? So it has a kinetic energy. So kinetic energy initial would equal 0. Kinetic energy final is not a vector, but it would be, there is kinetic. I'll just put, yes, there is one. This is just a scalar, but there is kinetic energy because this has got a velocity. See, so I would say rest, velocity equals 0, therefore kinetic energy initial equals 0. So it's velocity final at the end. It exists, so yeah, there's a kinetic energy. So this is connected to your velocity, or your speed, actually, I should say. So not moving to moving. And it's just in a straight line. We don't know why it's moving. Don't really care. We're not analyzing that. So let's look at the work done. The work happened somewhere along the line. Work was done on this. We don't know how. We don't know why. But we know it happened because you have work, which equals a change in energy. In this case, it's a change in kinetic energy. Now, just so you know, I'm going to go over here and do this. Work can be a change in energy. It can be a change in mechanical energy, which is potential and kinetic. It can be just a change in potential energy. It can be a change in kinetic energy. It can be a change in any kind of energy, but these are going to be the kind we're dealing with for right now. So just want to let you know any of that's possible. As long as energy's changing, work's happening. So, and if it's, for our purposes, as long as mechanical energy of some sort is changing, work's happening. So that's all we're worried about right now. So that's your work. Now look, work is also force times force dot displacement, force cosine theta displacement. We don't have a cosine theta. Let's just see, and this would be your displacement right there between these two, from here to here. So we don't have to worry about that dot product, the cosine theta right now. Let's just say force times displacement equals, well, let's go back up here and look at this. This is delta, change in K, so that's kinetic energy final minus kinetic energy initial, right? Well, look, no kinetic energy initial, so I'm just going to get rid of the final. I'm just going to say W work equals K. So we got our work, force times displacement, equals, I'm just going to put K, because that's just your final. I'm just going to call it, there's just one of them. All right, so you have that. So let's break this down a little bit more. Force is mass times acceleration times displacement. I'm just going to leave off. That's, stay there. Those are technically vectors, but not that huge a deal. And that's going to equal your kinetic energy. Let's come back to that. Go over here. I'm kind of giving this to y'all. You can actually plug this into one of your kinematic equations. Your final velocity squared equals your initial velocity squared plus 2 times acceleration times displacement. Okay, so see this? Right here, acceleration times displacement. See, it's right here too. Let's use that to connect these, to kind of bridge these problems, bridge these two equations together. And yeah, if it started from rest, your initial velocity is 0, and I'm just going to get rid of the final, just call that V, speed, actually. All right, so I'm going to solve this for the green part for AS. So I just divide by mass, divide by mass. So this means that you're right here. That's not my final answer. I'm just kind of showing you the acceleration times displacement is kinetic energy over mass. Remember, we're going to solve this for kinetic. In case you're unclear, we're solving this for kinetic energy. So you got speed, velocity, whatever, squared equals 2 times kinetic energy over mass. All right, now let's solve this for kinetic energy. I don't know why the m's don't like to stay. Okay, so we got to get rid of the m, so I'm just going to put that up here on the railroad tracks. Those kill each other. All right, I'll put room for this over here. So, and then I want to get rid of that 2 also. So this would actually be, let me get rid of that, the therefore symbol's in the way. We can fix this. Okay, so see how I just basically, this is m over 2, or mass over 2? That mass over 2. And that equals, all that had canceled out. So now I'm going to do therefore, and we're going to come up with the final one. Kinetic energy equals. Now, if you divide something by 2, it's just 1/2. This is how you'll usually see it written. I'm fine if you put it over 2. Just this is how you usually see it written. 1/2 mass, that's speed, because this is a scalar. I'm bad about not saying that sometimes. Mass speed squared. And that is how you find kinetic energy. That's mass speed squared. Just one thing I want to do on that real quick, and that is to prove the units. So let's look at this. Mass is measured in kilograms. This is a V for speed that's measured in meters per second. But if you notice, it's squared. And so you actually, when you square that, you square the meters and you square the seconds. And that is kilogram meter squared over second squared, which hopefully you know from the previous video. Yes, that is a joule. That is a Newton meter. That is a joule. So that is correct. And this is the last equation that you kind of, for right now, that you need on this. It is 1/2 mass speed, because it is a scalar, magnitude of velocity, squared.